In this lecture, I want to look at some more details related to the E2 reaction and provide some additional practice for us all. So when we do the E2 reaction, 91, okay. When we do the E2 reaction, what we have to remember is that we're looking for the adjacent, we're first of all recognizing our E2 base. Recognize the E2 base, and that's going to be these two species. And there are others, but these are the ones that I want us to worry about in this class. So we need to recognize our E2 base, and then we want to find the vicinal. These are often called Vic or Vis H atoms in our molecule. So okay, and so the vicinal hydrogens are, well, if we have C attached to bromine, and let's say we've got hydrogens, a hydrogen on the carbon directly attached to bromine, along with hydrogens attached to the carbon adjacent to that hydrogen, to that carbon with the bromine. What we have to recognize is that the hydrogen that's on the carbon that I usually label as a dot, this hydrogen is too close. This hydrogen is too close. So instead, what we have to do is count 3 bonds away, or maybe just get used to seeing the picture of when you've got your dotted carbon, you go to the carbon next door and see how many hydrogen atoms that it has. And so if we go ahead and look at an example of this, let's say we've got this molecule here and we're reacting it with potassium tert butoxide. We'll immediately cross out the potassium and put a negative charge on the oxygen atom. And then what we recognize is that we should find the adjacent hydrogen first, the vicinal hydrogen. It's adjacent also. Vicinal is a little bit more technically correct. We're going to attack the vicinal hydrogen, push the carbon-hydrogen electrons down to make a carbon-carbon double bond, and then push off the bromine. And that will give rise to this molecule as a product, plus some other things of KBr, plus tert butanol, but we don't need to worry about these. It's the organic product that we care about. Okay, so we want to be able to do this. We want to be able to recognize when we have our E2 bases present and then predict the product for reactions. Now, what I want us to recognize is there could be multiple vicinal hydrogens. What if there are multiple, and we've seen examples where there are multiple vicinal hydrogens, but it didn't matter which one reacted with the base. We get the same product in every case. So what if there are multiple vicinal H atoms? For example, if we had a molecule, and I'm going to have multiple types, that's what I meant to write, multiple types of vicinal H atoms. Let's say we've got this molecule here. Well, if we put the dot here, we've got 3 hydrogens on the methyl group reaching outside of the ring. Along with inside the ring, we've got 2 going down and then 2 going counterclockwise. Well, what I want to point out is that the 2 on the ring, these are actually all identical. And the 3 in green are actually different. So we have 2 different types of vicinal hydrogens. Of vicinal H atoms. Well, in that case, maybe you can guess this, you will have multiple products. In this case, we'll see 2, but you could have more depending on the symmetry of the molecule. Here we have a plane of symmetry slicing through the 6-membered ring, so the 2 going up are the same as the 2 going down. So you could have a more complicated scenario due to symmetry, and that's just going to give rise to more products. Now, the mechanism for all of these is the same. Mechanism is the same. But you just, but different vicinal hydrogens react with the base. Okay, so what does that look like in this case? I'm going to flip back and see what base I had. I'm not sure if I included one. Oh, I just drew the substrate. Okay, sorry about that. So I'm going to call one of the vicinal hydrogens A, and then I could call either of these other vicinal hydrogens B, just because they'll give rise to a product A and a product B. So if we had potassium tertbutoxide before, let's pick lithium diisopropyl amide this time. And so in this case, the negative charge is going to grab HA, oh, need my bromine, push the electrons down to make the carbon-carbon double bond, and then push the bromine off. And that's going to give what I'm going to label as product A. That way we can correspond this to our vicinal hydrogen that we remove. Now, what does that product look like? So what you can see here is I redrew all of the carbon atoms without the halogen. The halogen is left and it's gone. I'm going to draw a double bond between the halogen-containing carbon, what was the halogen-containing carbon, and the carbon that lost the vicinal hydrogen that reacted with the base by a deprotonation event. So product A is going to look like this. Now product B, if I redraw my starting material along with the apparent vicinal hydrogens, this is going to react with HB in this case, a different vicinal hydrogen, to make a different carbon-carbon double bond to push off the same halogen leaving group. Now I could have picked the one that was down from the bromine, or I could have picked the one going up, but these two products are the same. So either one I pick, just pick one, make sure you draw the correct number of products without duplicates, okay? So that's sort of the goal, is we want to find all of the adjacent hydrogen atoms and then draw all of the products corresponding to those adjacent hydrogen atoms. I could try to take a second to consider a very complicated scenario, but the very complicated scenario comes when our carbon attached to a bromine is attached to 3 separate carbon atoms. Okay, so now we have 3 different carbon atoms, and I'm not defining the stereochemistry on this, but now we've got 3 adjacent hydrogens over here. So I'm going to call these HA. 2 adjacent hydrogens over here. I'm going to call each of those HB, and then 1 adjacent hydrogen over here. It's going to be HC. So we still have just 3 adjacent. We just have 3. Just want to make sure I want to do this. I'm okay with it. I'm okay with it if you are. There's one little hitch in this example that we'll learn more about in organic chemistry too, but that's okay. Okay, so in this case, what we want to do is then draw the product for removing each of the adjacent hydrogens. So HA is going to be removing this one, making a new carbon-carbon double bond, and then adding or losing the bromine, excuse me. That's going to give this product as A. You could show a product as B. Now B's actually got an issue. So B's actually got an issue. There's actually 2 products for B. At this point in the semester, I need to teach you about alkene stereochemistry to see these 2. I don't want to put this on an exam, but I'll be correct now. There's actually 2 products for B because these 2 are different because there's not free rotation over the carbon-carbon double bond. Anyway, let's move on. Let's go to C. Let's say then I took C's vicinal hydrogen, pushed its bond down as opposed to B or A to make a carbon-carbon double bond to the isopropyl unit. and that would give rise to this molecule. Okay, so B would be something that's a little bit too far beyond the scope of where we're at, but I could have picked a better example, like maybe there was a cyclohexyl going to B or something. But anyway, here's a more complicated example showing you the many types of products that could be formed. It doesn't get too out of control as long as you're good at defining and locating the adjacent hydrogen atoms. Okay, so with that, I think we'll look at one more video to do some deeper mechanistic work on the reaction, but otherwise that'll do it for the practice, and there's practice on the discussion problem set.